Hi everyone, this is P for Physics. Welcome to another session. This is me, Joe. In the previous session, we have been discussing about charges. We have started to discuss about charges. We were able to understand that there are two types of charges, positive charge and negative charge. And we said we shall concentrate on the basic properties of charges in the coming session. And that happens to be this. Before jumping into the basic properties of charges, let us ask ourselves or let us try to have some clarity about charges. We now know for sure that charges are the most fundamental concepts when it comes to electricity. Electricity is a part of electromagnetism. So our understanding about charge and its clarity is very, very essential in order to understand electromagnetism. When you take an object, if I ask you a question, what are the different states of matter? It would be an easy question to answer, right? Because right in our 5th grade or 6th grade, our teachers would have introduced about the different states of matter, solid, liquid and gas, right? If I ask you, what is meant by mass? Define mass. Because whenever we talk about these 3 states of matter, whenever we talk about matter by itself, mass is an important property that we talk about. That is the primary thing that we concentrate on whenever we talk about matter, right? So when I ask you what is meant by mass, we would come up with a definition like mass is the amount of matter contained in an object. So mass is the way in which we are talking about the materialistic aspect of matter. The concept of mass is nothing but the materialistic point of view of matter. There are other properties of matter as well. One of the important property is electrical nature of matter. When we talk about electrical nature of matter, charges come into play. So when we try to answer what is meant by an electric charge, this is what we might come up with. Like mass, electric charge is another intrinsic property of particles. When I say a particle, for example, let us take an electron, which happens to be a particle, a subatomic particle, which we are very familiar with, or maybe a proton, which is another subatomic particle. When we talk about the materialistic aspect of that particle called electron, we would have a value. This is the mass of an electron, which has been already found. And when we talk about the charge of that particle, we would say it is negatively charged. So, a particle has materialistic perspective as well as electrical perspective. In the materialistic perspective, we talk about its mass, and in the electrical perspective, we talk about its electric charge. So this is the basic idea of electric charge. And the SI unit of electric charge is said to be Coulomb. Coulomb is named after a scientist, therefore it is represented with a notation of capital C. When I start to talk about basic properties of charges, a question might rise in your mind. That is, you are saying that you are going to talk about the basic properties of charges. But I know that there are 2 different types of charges, positive as well as negative. And what basic property are you trying to say? Is it for positive charge? Is it for a negative charge? This might be the question that come up in your mind. So remember, whatever we are about to see in this session are the basic properties of charges in general. It refers to both positive and negative charge. The first important property happens to be conservation of charges. I used to tell my students, whenever we talk about a topic, whenever we deal with a topic in physics, it is better to comprehend that topic in the linguistic sense initially rather than the scientific sense. So conservation of charges. When I ask you, what is meant by conservation? I mean, the mere meaning of it, the synonym of conservation in the pure linguistic sense. We might say conservation means, say, preservation, maintaining something without changing. So this is all the meaning that this English word conservation might give us. And when I say conservation of charges, I get a vague meaning that maintaining the value of charges or preserving the charges. So in physics, we often use a term called a system. Let us try to have a basic idea of what is meant by a system. When we talk a system is actually a fancy term we use in physics. Whenever we are investigating something, whenever we are interested in something, that is called a system. Let us say, for example, if you are going to investigate a table which is by your side, that table is your system and everything else apart from the table is its surrounding. So this is the idea of system in physics. So when we fix something as a system, everything else becomes the surrounding. In the historical point of view, in the previous session, in the historical perspective, historical background, we were trying to talk about charging, right? And we were seeing one or two combinations in which just by the act of rubbing, the charging taking place. If we could remember the previous session, this diagrammatic representation, a very small diagrammatic representation, gives us a glimpse of what we discussed in the previous session. We were talking about the combination of glass rod and silk cloth, right? So in this diagrammatic representation, my interest is to represent what happens during the act of rubbing. I have neither drawn any charge, be it positive or negative, neither in the glass rod nor in the silk cloth. That doesn't mean that they don't have charges. There are millions and billions of charges in reality with every object that we come across, because there are millions and millions of atoms. They consist of subatomic particles, both protons and electrons. Therefore, the charges are abundant when it comes to any object that we come across. So here, I have represented visually what happens during the act of rubbing. From the arrow marks marked here, we are able to understand that glass rod during the rubbing loses or donates few negative charges to be precise, to the silk cloth. That is, the act of rubbing here has the glass rod to lose 3 charges and thereby the silk cloth gaining those 3 charges. Though they are composed of millions and billions of charges, for simplicity, for simple math, let us assume that the initial number of charges in the glass rod were 10 and the same with the silk cloth. So initially, if I say the glass rod is not rubbed with silk cloth, I may consider the glass rod as a separate system and silk cloth as another system. But now then, since they have made physical contact with each other, because I have rubbed the silk cloth with the glass rod, I consider that as a single system. So in that case, if I ask a question, how many number of charges are present, or what is the total charge or net charge of the entire system of glass rod plus silk cloth, we would easily come up with an answer. 10 plus 10 is 20. So here, what happens after rubbing? Whatever the count that I have mentioned here is before rubbing. There were 10 charges in the glass rod, 10 charges in the silk cloth. And after the act of rubbing, since the glass rod has given away 3 charges and silk cloth has gained those 3 charges, now the value changes, the proportion changes. By donating or giving away 3 charges, glass rod from 10 reduces to 7. On the other hand, silk cloth from 10, since it has gained 3 more charges, 3 more electrons, becomes 13. So by donating or losing negative charge, the overall value of glass rod becomes more positive. Therefore, we say glass rod by rubbing with the silk cloth becomes positive. On the other hand, since silk cloth is gaining the negative charges, the overall negative aspect of this negative charge of the silk cloth is increasing. Therefore, it becomes negative. Why do I explain all these stuff now? What we are talking as conservation of charge is closely related with what we have illustrated here. So when we talk about rubbing, what has rubbing really done with the glass rod or the silk cloth? We are sure rubbing doesn't create charges because initially it was 10 plus 10 and now the ratio has changed, but it remains the same as 20. 7 plus 13 is again 20. This gives us a very important and practical understanding that the act of rubbing has not at all created a charge, even a single charge, but it has only transferred it from one object called the glass rod to another silk cloth. So the act of rubbing doesn't create charges, but only transfers them. So in other words, we are able to understand that we cannot create charges. The same goes with destroying. We can't destroy a charge as well. So creating a single charge or destroying a single charge is impossible. In that case, if we try to just extrapolate this idea, here it is a glass rod and silk cloth combination. And if we talk about if we try to assume the total number of charges present in the entire universe, take it from me, it's an unimaginably larger number. It's a vast count. It's infinite. We don't know the exact count, but we know for sure about one thing, that I am not able to create even one charge, nor destroy one. In that case, we will be sure that always, the total charge in the universe remains a constant. The total charge in the universe is always a constant. This in turn means charge is conserved in nature. Charge is conserved if put into the form of a law could be called as law of conservation of charges. This rings some bell in our mind, right? Because in our lower classes, we would have studied about law of conservation of energy, for instance. There are a lot of conservation laws which we have come across up to the 10th standard. And one of the important thing is law of conservation of energy. Even now, we might easily say the statement of it. Energy can neither be created nor be destroyed, but it can be transformed from one form to another. Similarly, if I want to put forward the law of conservation of charges here, which is the law statement of this idea of conservation of energy, it might mean that charges can neither be created nor be destroyed. Perhaps we could add some more points, one more point, but it could be transferred from one object to the other. So, now what would be the net change in charge? So, in the same example, what is the net change in charge? When we do the simple math, 10 plus 10 is 20, and after rubbing it becomes 7 plus 13, okay with the difference in numbers, but the total value remains the same. 7 plus 13 is again 20. So if I ask the question, or if I want to answer the question, what is the net change in charge? Man, there is literally no change. It was 20 initially, and now too it is just 20. Perhaps the places got transformed. It jumped from glass rod to the silk cloth. Of course, it cannot jump. It moved from. So the net change in charge is always zero. This is another important point that we should talk or remember with relation to this idea of conservation of charges. So the next thing happens to be quantization of charge. This is the second basic property of charges that we are going to discuss about. Quantization of charge. In this title, the word quantization might seem new to us because we aren't familiar with quantization so far. At least in physics, we haven't come across this term. What is meant by quantizing something? Like we tried to have a literally comprehension of the word conservation a little ago. If we want to understand what is meant by quantization, so quantization of charges, let us assume that the particles bear one of the property of charge. The electrical property is literally said to be charge, and the materialistic property is said to be mass. Few minutes ago, we were talking about electrons, right? And if I ask you how many electrons are there in a particular atom, and let us say the number is 10. And if I ask you to distribute or to give away 4.5 electrons to me, what would you think about me? Oh, this guy is so crazy. How can I give 4.5 electrons, man? Because it can only be a complete value. Ask either 4 or 5, so I can give you. But if you ask me 4.5, I cannot give away 4.5 electrons because that is practically not possible. The same thing goes with the charges. Quantization of charge simply means that the value of charges can take only certain allowed values and it cannot take any random value that it wishes. It takes only discrete values. Discrete means specific values that are allowed by certain rules and regulations. So quantization of charge simply means the charge Q on any object. So here let us replace this idea of object with the system we were talking about. And charge automatically refers to the total charge or the net charge of that system. Now let us read it again. Charge Q on any object is equal to the integral multiple of fundamental unit of charge E. So E happens to be the fundamental unit of charge. What is that fundamental unit of charge? In our example of 10 electrons in hand, the fundamental unit of 1 electron is E. If it is positive, it could be represented as plus E. If it is negative, it could be represented as minus E, but the value of E is the fundamental value. Fundamental unit of charge is the smallest possible value of any charge in nature. And the total charge could be easily found by multiplying the fundamental unit of charge with the number of charges available in that so-called object or system. This is the basic idea. If I want to mathematically represent what we have just seen into the form of a formula or equation, it could be something like this. This happens to be the first ever equation in electrostatics or 12th grade physics. This is the first equation. We very well know that physics and equations are inseparable, and this happens to be our first equation. Q is equal to NE. Now that we know what is Q, the net charge or charge on any object is Q, and E happens to be the fundamental unit of charge. If so, what is N? N is merely an integer. Since N can only have full values, that is 1, 2 or 3, it could be any integer possible, and no decimal values are possible here because in the example we clearly have understood that it is impossible to separate masses into half, a quarter or something like that. It can only be a complete value. So when we talk about Q is equal to NE, and if I say the value of N is 5, I mean to say that the total charge of that object is actually 5E. Substituting N for 5 will give me 5E. If I know the value of the so-called fundamental unit of charge, just by multiplying that integer 5 with that value of E, I'll be able to calculate or say what is the total charge of that object, and for which I need to know E, right? And thanks to Millikan's oil drop experiment, which we would later discuss in the atomic physics in detail, for now let us take up the result. A physicist called Millikan has given us a beautiful value, the constant, first ever constant in this 12th grade again. We come across a lot of constants in physics. So E, the fundamental value of a charge, is equal to 1.6 into 10 power minus 19 coulomb. Remember here the value is 10 to the power minus 19, which is a very, very, very small value. Knowing this, now it becomes easy for us to calculate the charge on any object easily using the equation Q is equal to NE. And we were talking something about quantizing the charge, right? This equation is the mathematical representation of the quantization of charge, or Q is equal to NE. Just give us an understanding that charge is quantized you cannot have any desired value of a charge, but it can only take certain discrete values or allowed values alone. Now that we are talking about electric charges, its basic property, we very well know any physical quantity can be categorized into two. One is a scalar quantity and the other is a vector quantity. Now a question may arise in our mind, is electric charge a scalar quantity or a vector quantity? This question might arise because that negative or positive charge confuses us with vectors. Because in vectors too, we have directions where we use plus and minus signs. Now, if someone asks you whether electric charge is a scalar quantity or vector quantity, be sure to say it is only a scalar quantity. Electric charge is always a scalar quantity where the negative sign or positive sign just represents its type of charge and it has nothing to do with the vector value. So this is another important point that we should club with the idea of quantization of charge. And the other important basic properties of charges is additive nature of charge. So here we were trying to calculate the total charge of an object. And if we want to add charges, I said 5e, that is actually a value. And if I have three positive charges in a particular object and 5 negative charges in a particular object, how many charges are there in total? We would say it is 3 plus 5. And I cannot use 3 as such and 5 as such because I have said one is positive and the other is negative. Therefore, I should use them along with the sign. So along with the signs, we would be doing simply algebraic addition and not ordinary addition. So additive nature of charge talks about considering the charges along with their signs, positive or negative. And when I have 2 charges, positive and 2 negative charges in a particular object, what is the net charge or total charge of that object? It could only be 0 because minus 2 plus 2 would be only 0. So if I want to have additive, that is how we talk about the additive nature of charge. And when we talk about charges, we know if it is an electron, it is going to revolve around the atom. Right, in the Bohr's atomic model, we have been taught that if a charge is moving, will the speed of the charge or the speed of the body change the magnitude of charge? Let us say there is an object which is continuously in motion and it is going with a velocity v. Will that velocity affect the value of magnitude of charge? No, certainly not. Magnitude of charge is independent of speed of the body. This is also a very important understanding that we should have. So now that in this discussion, we have been jumbling between mass and charge, since they happen to be both the basic property of the same matter. Now let us try to have a better idea of what the charge and mass comparison. We have been talking about mass, we have been knowing about mass. Now that we have learned something more about electric charges. So if I try to compare electric charge and mass, I'm trying to compare things and I'm not trying to find differentiation between the two. Both are done here. Let us try to compare the aspects of an electric charge as well as mass. When we talk about electric charge, we know for sure it can either be positive value or it could take a negative value. That depends on the type of charge we are talking about. But in case of mass, it is always a positive quantity because a negative value for a mass is unimaginable. It is not practical, right? I cannot have minus 50 kg. I can only have plus 50 kg. So it is always a positive quantity. And just now we talked about the association of speed of the body and the value of the charge. We have understood that the electric charge is independent of the speed of the body. The speed of the body does not affect the value of charge, but in case of mass, it is not the same. The relativistic mass increases with speed of the body. Maybe this relativistic mass seems a new idea to us. We shall later reserve it for relativity. Now you understand that mass is said to be constant, but what is said to be constant is not just mass, but the rest mass of any object. The relativistic mass, that is, the value of mass with respect to the speed of the body, is called relativistic mass, and that relativistic mass increases with the speed of the body. The more the speed of the body becomes, the more is its relativistic mass. So it is dependent on the speed of the body. And we know for sure that charge is quantized because we have been discussing about Q is equal to NE just a few moments ago, right? And in this same case, like electric charge, is mass quantized? No. Quantization of mass is known to us yet. We don't know whether it is or how to quantize mass or not. Quantization of mass is not yet known to us. And charge is always conserved. We have studied about the conservation of charges. But mass is not conserved because it can be converted into energy. So the most famous equation in entire physics is E is equal to mc square, which happens to give us the idea about the connection between mass of an object and the energy associated with it. Since E is equal to mc square, we know for sure that mass can be converted into energy and vice versa. In that case, I cannot preserve mass. So that is what we mean to say mass is not conserved. And when we talk about electric charge, the force between two charges is either attractive or repulsive. That depends what type of charge meet at a place, and that decides what type of force that is going to exist between them. So it is going to be either attractive or repulsive. But when it comes to masses, what is going to happen between two masses? Only gravitational attraction, gravitational pull. So the force between two masses is always attractive. Well, with this, let us close this session and we would meet in another session. Remember, this is P for Physics, where we would try to learn and enjoy physics. Try to subscribe for it if you haven't done it. And if you like the video, please press the like button and tell your friends about P for Physics. So without you, we can't grow, and we would like to connect with you. And let us explore more and more physics in the days to come. Friends, if you got any comments, please share it in the comment section. And this is Joe signing off. See you in the next video. Take care. Thank you.